Hello friends, in the previous discussion we learned that the second law of thermodynamics leads to the definition of a new property called entropy, which is a quantitative measure of microscopic disorder for a system. Then we talked about the increase of entropy principle, entropy change, and finally we learned that the effect of irreversibilities is always to increase the entropy. In today's discussion, we shall be talking about entropy change of pure substances, isentropic processes, property diagrams involving entropy, and the third law of thermodynamics. Entropy change of pure substances. Entropy is a property, and thus the value of entropy of a system is fixed once the state of the system is fixed. Specifying two intensive independent properties fixes the state of a simple compressible system and thus the value of entropy as well as the value of other properties at that state. Starting with its defining relation, the entropy change of a substance can be expressed in terms of other properties, but in general these relations are too complicated and are not practical to use for hand calculations. Therefore, using a suitable reference state, the entropies of substances are evaluated from measurable property data following rather complex computations, and the results are tabulated in the same manner as other properties such as V, U, and H. The value of entropy at a specified state is determined just like any other property. In the compressed liquid and superheated vapor regions, it can be obtained directly from the tables at a specified state. In the saturated mixture region, it is determined from S is equal to SF plus X SFG. Here X is the quality and SF and SFG values are listed in the saturation table. In the absence of compressed liquid data, the entropy of the compressed liquid can be approximated by the entropy of the saturated liquid at the given temperature by this expression as S at the rate Tp is approximately equal to SF at the rate T. The entropy change of a specified mass m during a process is simply delta S is equal to m delta S and is equal to m into S2 minus S1, which is the difference between the entropy values at the final and initial states. When studying the second law aspects of processes, entropy is commonly used as a coordinate on diagrams such as the TS and HS diagrams. This figure here shows the general characteristics of the TS diagram of pure substances using data for water. Notice from this diagram that the constant volume lines are steeper than the constant pressure lines, and the constant pressure lines are parallel to the constant temperature lines in the saturated liquid vapor mixture region. Also, the constant pressure lines almost coincide with the saturated liquid line in the compressed liquid region. Isentropic processes. As mentioned earlier that the entropy of a fixed mass can be changed by heat transfer and irreversibilities, then it follows that the entropy of a fixed mass does not change during a process that is internally reversible and adiabatic. A process during which the entropy remains constant is called an isentropic process. It is characterized by delta S is equal to 0 or S2 is equal to S1. That is, a substance will have the same entropy value at the end of the process as it does at the beginning if the process is carried out in an isentropic manner. Many engineering systems or devices such as pumps, turbines, nozzles and diffusers are essentially adiabatic in their operation, and they perform best when the irreversibilities such as the friction associated with the process are minimized. Therefore, an isentropic process can serve as an appropriate model for actual processes. Also, isentropic processes enable us to define efficiencies for processes to compare the actual performance of these devices to the performance under idealized conditions. It should be recognized that a reversible adiabatic process is necessarily isentropic, but an isentropic process is not necessarily a reversible adiabatic process. The entropy increase of a substance during a process as a result of irreversibilities may be offset by a decrease in entropy as a result of heat losses, for example. However, the term isentropic process is customarily used in thermodynamics to imply an internally reversible adiabatic process. Property diagrams involving entropy. Property diagrams serve as great visual aids in the thermodynamic analysis of processes. Consider the defining equation of entropy. ds is equal to delta Q upon T internally reversible. It can be rearranged as delta Q internally reversible is equal to T ds. As shown in figure, delta Q internally reversible corresponds to a differential area on a Ts diagram. The total heat transfer during an internally reversible process is determined by integration of Tds from 1 to 2 as given by this equation. This corresponds to the area under the process curve on a Ts diagram. Therefore, we conclude that the area under the process curve on a Ts diagram represents heat transfer during an internally reversible process. This is somewhat analogous to reversible boundary work being represented by the area under the process curve on a PV diagram. Note that the area under the process curve represents heat transfer for processes that are internally or totally reversible. The area has no meaning for irreversible processes. As an isentropic process on a Ts diagram is easily recognized as a vertical line segment, this is expected since an isentropic process involves no heat transfer, and therefore, the area under the process path must be 0. The Ts diagram serves as a valuable tool for visualizing the second law aspects of processes and cycles, and thus they are frequently used in thermodynamics. Another diagram commonly used in engineering is the enthalpy entropy diagram, which is quite valuable in the analysis of steady flow devices such as turbines, compressors and nozzles. The coordinates of an HS diagram represent two properties of major interest: enthalpy, which is a primary property in the first law analysis of the steady flow devices, and entropy, which is a property that accounts for irreversibilities during adiabatic processes. In analyzing the steady flow of steam through an adiabatic turbine, for example, the vertical distance between the inlet and the exit states delta H is a measure of the work output of the turbine, and the horizontal distance delta S is a measure of the irreversibilities associated with the process. What is entropy? It is clear from the previous discussion that the entropy is a useful property and serves as a valuable tool in the second law analysis of engineering devices. But this does not mean that we know and understand entropy well, because we do not. In fact, we cannot even give an adequate answer to the question, what is entropy? Not being able to describe entropy fully, however, does not take anything away from its usefulness. We could not define energy either, but it did not interfere with our understanding of energy transformations and the conservation of energy principle. Granted, entropy is not a household word like energy, but with continued use, our understanding of entropy will deepen and our appreciation of it will grow. The next discussion should shed some light on the physical meaning of entropy by considering the microscopic nature of matter. Entropy can be viewed as a measure of molecular disorder or molecular randomness. A system becomes more disordered, the position of the molecules becomes less predictable and the entropy increases. In the solid phase, the molecules of a substance continually oscillate about their equilibrium positions, but they cannot move relative to each other, and their positions at any instant can be predicted with good certainty. In gas phase, however, the molecules move about at random, collide with each other and change direction, making it extremely difficult to predict accurately the microscopic state of a system at any instant. Associated with this molecular chaos is a very high value of entropy. When viewed microscopically from a statical thermodynamic point of view, an isolated system that appears to be at a state of equilibrium may exhibit a high level of activity because of continual motion of the molecules. To each state of macroscopic equilibrium, there corresponds a large number of possible microscopic states or molecular configurations. The entropy of a system is related to the total number of possible microscopic states of that system, called thermodynamic probability P by the Boltzmann relation expressed as S is equal to K log of P. Here K is equal to 1.3806 into 10 raised power 23 and is the Boltzmann's constant. Therefore, for a microscopic point of view, the entropy of a system increases when the molecular randomness or uncertainty, that is molecular probability of a system increases. Thus, entropy is a measure of molecular disorder, and the molecular disorder of an isolated system increases anytime it undergoes a process. The third law of thermodynamics. As mentioned earlier, the molecules of a substance in solid phase continually oscillate, creating an uncertainty about their position. These oscillations, however, fade as the temperature is decreased and the molecules supposedly become motionless at absolute zero. This represents a state of ultimate molecular order and minimum energy. Therefore, the entropy of a pure crystalline substance at absolute zero temperature is zero, since there is no uncertainty about the state of the molecules at that instant. This statement is known as the third law of thermodynamics. The third law of thermodynamics provides an absolute reference point for the determination of entropy. The entropy determined relative to this point is called absolute entropy, and it is extremely useful in the thermodynamic analysis of chemical reactions. Molecules in the gas phase possess a considerable amount of kinetic energy. However, we know that no matter how large their kinetic energies are, the gas molecules do not rotate a paddle wheel inserted into the container and produce work. This is because the gas molecules and the energy they possess are disorganized. Probably, the number of molecules trying to rotate the wheel in one direction at any instant is equal to the number of molecules that are trying to rotate it in the opposite direction, causing the wheel to remain motionless. Therefore, we cannot extract any useful work directly from disorganized energy. Now consider a rotating shaft shown in this figure. This time the energy of the molecules is completely organized, since the molecules of the shaft are rotating in the same direction together. This organized energy can readily be used to perform useful tasks such as raising a weight or generating electricity. Being an organized form of energy, work is free of disorder or randomness and thus free of entropy. There is no entropy transfer associated with energy transfer as work. Therefore, in the absence of any friction, the process of raising a weight by a rotating shaft or a flywheel does not produce any entropy. Any process that does not produce a net entropy is reversible, and thus the process just described can be reversed by lowering the weight. Therefore, energy is not degraded during this process and no potential to do work is lost. The quality of energy is always preserved during an actual process, that is the first law, but the quality is bound to decrease, that is the second law. This decrease in quality is always accompanied by an increase in entropy. As an example, consider the transfer of 10 kilojoules of energy as heat from a hot medium to a cold one. At the end of the process, we still have the 10 kilojoules of energy, but at a lower temperature and thus at a lower quality. Heat is in essence a form of disorganized energy, and some disorganization, that is entropy, flows with heat. As a result, the entropy and the level of molecular disorder or randomness of the hot body decreases with the entropy, and the level of molecular disorder of the cold body increases. The second law requires that the increase in entropy of the cold body be greater than the decrease in entropy of the hot body, and thus the net entropy of the combined system, that is the cold body and the hot body, increases. That is, the combined system is at a state of greater disorder at the final state. Thus, we can conclude that processes can occur only in the direction of increased overall entropy or molecular disorder. That is, the entire universe is getting more and more chaotic every day. So friends, here we come to the end of our discussion, and therefore we sum up. Entropy change is caused by heat transfer, mass flow and irreversibilities. Heat transfer to a system increases the entropy, and heat transfer from a system decreases it. The effect of irreversibilities is always to increase the entropy. Heat is in essence a form of disorganized energy, and some disorganization will flow with heat. The entropy and the level of molecular disorder or randomness of the hot body decreases with the entropy, and the level of molecular disorder of the cold body increases with entropy. The second law requires that the increase in entropy of the cold body be greater than the decrease in entropy of the hot body, and thus the net entropy of the combined system increases. Processes can occur only in the direction of increased overall entropy or molecular disorder. So that is it for today. In the next lecture, we shall be discussing more about entropy. Thank you very much.